They try to sell your body and your soul. It's the price you pay for rock and roll. And no one understands it, how you feel. For it's so unreal. Oh, it's so unreal. Baby, don't you cry for me. It's an illusion, just an illusion. I thought I knew what life should be. It's an illusion, just an illusion. Critics crucify your latest show. Another drink and then you lose control. And then on stage I feel a fire burn. There is no return. I'm always on the run. I give it to you, babe, with all my heart. For it's not.
All right, so sometimes well, we played some Just an Illusion, and today I'm going to tell you some illusion that we created in your computer system, and then you're probably feeling like, yeah, I'm living in a fake world, but in fact, you have been living in a fake world for a while. The only thing that I know for sure is like what I have on my shirt. Life cannot be reset. All right, so let's get started. But before we start continuing our series on the topic that we are going to talk about today, it's always a good idea to remind ourselves where we are coming from. So the very first thing that you have to remember, finally, not von Neumann architecture, right? So, but it's still related to von Neumann architecture in a way that in a joint block of von Neumann architecture that we have the memory hierarchy, and the memory hierarchy pretty much looks like this. We have a processor with the fastest storage code register, and then we have the SRAM in between your register and DRAM. And the reason because of that is because there is a huge gap between the register speed, which is aligned with your processor speed. And to mitigate that gap, we build multiple labels of memory hierarchy. And the good thing is that because your code has locality, so hopefully if we if we write our code carefully and if the hardware is designed properly, then most of the time we don't need to access the DRAM, which is very slow. And that's the whole idea of why we have this series of lectures. However, sometimes I need to sometimes when I write code, right, I cannot imagine there are lots of magic happening behind. So for example, like this pieces of a code, you think, well, this is very elegant, one single for loop, and it's just one line of code that people easily know what I'm doing. However, because of the underlying architecture only has four-way set associativity. So it turns out that this pieces of code has a lot of conflict misses in addition to the compulsory misses that are non-avoidable. So there are several optimizations to address this type of question. So for example, we have learned loop interchange, which is an idea that we can change the order of the loop to make sure that the loop is traversal in a way that it fulfill the locality or say the way how cache store blocks. And the second type of optimization is to address the question that we have for the NVIDIA Tegra that what if we don't have sufficient amount of weight associativity? So the idea of a loop fission is that, well, instead of putting everything inside a single iteration, we have to separate it out so that during each iteration or say each given time frame, we only access limited amount of data structures. So hopefully we can avoid the conflict misses. And finally, there's loop fusion. So as you can think, right, why don't we like the idea of this loop fission? Because it separates things into two loops. So apparently you are going to have more instruction counts, you are going to have more branches, you are going to have more memory accesses. So if your hardware allows you to fill stuff into a single iteration, why not doing it? However, when to fission, when to fusion, that's completely depending on which processor you are using. So that's why being a programmer, you have to be aware of what's happening below your code. So today we are going to continue our series on studies on software optimizations. And then I'm going to tell you about the illusion of memory system in our computer architecture. So in the last lecture, we talked about the matrix multiplication. Apparently, the matrix multiplication is important, but if you don't write it carefully, it's actually easily underperforming. So for example, the first type of miss you are going to interact is called capacity miss, because think about the case that we demonstrated. If I have a matrix of 2K by 2K, then it turns out that every time in matrix multiplication, you have to fetch a row and a column. So even though I haven't finished traversing the whole matrix, just a few rows and a column is good enough to get my cache filled. So that's definitely not the case we want. So that's one issue with the matrix multiplication. And another issue which is not clear, the last time some people were asking me about, well, why we have the conflict misses. So again, in a lot of cases, which we refuse to do the cache simulation because we thought our brain is good enough. However, there are cases that you definitely have to do cache simulation. So if you pay attention to the notebook that I put on GitHub, it's definitely giving you some easy way to get that out. So I tweaked the demo we have in the last lecture a little bit to help address your issue with that. So the thing is that now I have a compilation flag code. If it defines dump, then I will print out the address that has been traversed through each loop. And what happened is that, okay, so now I make a dump, and then now I'm only traversing a 256 matrix, 256 by 256, which is a lot smaller. And it will produce the address and in this CSV file. However, and then here is some Python code that helps you to, and essentially it's use C equal to ABS to figure out what are the partition of the address. So if you are interested, it's definitely something that you can try out, and it probably would accelerate the speed that you are doing your homework, by the way. So the thing is that, right, here I'm only printing out, well, we are traversing 3 matrices. Here I'm only printing out B. right? Thinking about the case that we are doing C equal to B, A times B. So for the A, it's a row, right? And we already know that a row is probably about like 2K. Well, so for 256, then it's about, what size of it? Yeah, it's also about 2K, 2K bytes, right? So it's, first of all, a row definitely fits in the cache, right? So in this case, so now let's print out the address of B, which is the column. And turns out that C, after partition the address, you will figure out that here's the tag, here's the index. So for B00, it's index 0. B10 is index 20. And then B20, it wraps back again to 0, right? So let's count, right? So now I'm going to 4, 0, 0, 0, 0, 0, 0, 0. How many zeros we have interfaced so far? It's 8 already, right? And this is the 9th. And this is an A-way set associativity cache. So what's going on? What's going on? What should I be doing now? So I have this in index 0, 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 square 8. And well, and then now, what's about this? What am I going to do? Do I still have space in index 0? Do I still have space in index 0? No. Then what am I going to do? Well, I have to kick out B00, right? So what happened is when the next time I want to access B01, which is the column right next to B00. What kind of miss am I going to see? Conflict miss, right? So the thing is, right, if your address sequence is, I'm worried about your midterm now. Okay, so the thing is that, right, like, okay, so the address sequence of B0 looks like this. And at this point, we are going to kick someone out. And the thing is that, right, if you look at the data that we just used for the B matrices, it's only 17 elements. So it's way smaller than the cache size. So by no means is a capacity thing, right? So here I have some, and then, well, so the thing is that this miss itself is not a conflict miss. This miss is a capacity miss. But what happened is that because of that, we are going to kick out stuff. So later on, if we revisit the same block of B, there are always going to be conflict misses. You know what I'm saying? Okay, so the thing is, right, here, you have to be really, so that's why we want the block algorithm to restrict the size of working set that we are visiting within a given time frame. Otherwise, you will generate a lot of conflict misses like that. Right. So you have to take that into account when you write your homework. Say, some people saying that, well, what's the end of the block algorithm? And this end is indeed like, what's the partition that you want to use for your matrices, and it should vary. It should vary by the size of your matrix. So you cannot put a fixed number there and hope it's working for every size, right? So just want to let you know that programming assignment is not easy, and you have to tune a number many times to get it right. All right, so so that's why it removes both capacity and conflict misses, because we have shown you that that's the source of conflict misses, and capacity misses. I think you already know why it is that. Okay, so one more question for you. So Now, I am going to make the matrix multiplication even faster, but the way how I make it even faster is actually this. I add some more overhead before running the matrix multiplication, which is the matrix transpose. So the idea of matrix transpose, I think everyone knows that, right? So after I transpose the matrix, right? Originally, I am multiplying a row and a column, but after I transpose it, it could be multiplied row by row, right? So you can imagine, wow, there are huge benefits here, right? So I just want to ask you, what kind of benefits do you think we can take from adding the matrix transpose code before running the matrix multiplication? Hmm? Oh, no, I mean, it's okay. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Huh. Definitely some kind of discussion. So go. Um, I forgot to put a timer, but you can still vote. All right, let's wrap up in 15 seconds. Sorry, one more time. Let's wrap up in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, what do you guys think? Huh. So still kind of diverse, huh? C or E. So what's C? What's E? C is conflict miss and E is compulsory miss. So yeah, why? Can somebody tell me that? What do you think? You chose B. Okay. What else? Why do you think it's B?
You can compare the old algorithm and the new one, what improved is that it is count not by row, it's all count by column.
Yeah, but the number of elements that I traversed, is that different? What's capacity miss?
Compared if the whole cache line is full and you are adding more new elements and its old ones are kicked out, I think
That's a not capacity miss.
What?
That's a not capacity miss. What's capacity miss?
Capacity. So capacity means might be the site number is not enough for.
The total capacity of your cache is not enough. Right. And you are saying that we start to kick out because the number of blocks we don't have, that's not precise. And it also sounds like a conflict miss. Right. So you have to be precise. All right. So not capacity miss. What else? Why is it why does that help conflict miss? Do you remember our slides? A few slides ago? Like here. Why we have conflict misses? Does it? Okay. So it changes the indexes. When you say indexes, is the index of this, or how does that change? Okay, so here's the thing, right? If you traverse the B matrices in this order, right? It's many of the elements within different blocks, right? And the reason why it's a different block is that if you look at their tags are all different. So they are different blocks, right? So that's why when they map to the same index, one will kick out, maybe a later one will kick out an earlier one. So when we revisit the element like B01, it's not going to be there anymore, right? So when we access B01, that's a conflict miss.
First, one question: why are you sure that all the index are well?
You were missed the class. It's actually generated by the program. I run it, and it's the address produced by the program, and I partition it. Are you convinced now? It's on a notebook, you can run it. Okay.
Yeah, so I just have so I just have one quick question.
Uh-huh.
So it's like the program will assign the address first, and so we transfer the to the tag and index, right?
Yeah.
Well, the thing is, so it's like B0 and B10. So it's like it's just change 2 digits. It's just adding 216. So it's like the last 3 digits of the B0 is 000 and B01.
So this changes program by program, right? And for our case, right, this demo is run assuming that you have a 256 by 256 array, right? So each dimension has 256 elements, and each element is 8, right? So you turns out have 2 to the 8 times 2 to the 3. So every time you change a row, it will change the address by 11 digits, right? And 11 digits is actually like it's actually like 800 in hex, right? So that's why you see the address is different by 800 every time when you change your row, right? And because of that, right? So you have multiple the same column belonging to different blocks. They all map to the same set. So that's where the conflict misses are coming from. But if you change the order of traversing, turns out that all of them will be in the same block. And even though I am going to the next block, as you said, the next block would probably start with index 0x1 instead of mapping to 20, keep wrapping around 0 and 20. So that's why all the conflict misses are gone. Make sense? So go back to that. Do we have capacity misses if we partition the block carefully? Or does the transpose change anything regarding to the capacity misses? Well, that's not the right answer, right? You say conflict miss will happen more often. That's not the right answer, right? That's not a precise answer. So the thing is, right, it's capacity miss, right? Again, you have to think about how much data that how many elements that I have traversed, right? And comparing this one and this one, right? Still the same number of, like, I didn't change this array size at all. I didn't change the n at all. So still completely the same block size, the same tile size. So in terms of the capacity or the working set size, it doesn't change at all. Agree? So there is nothing to do with capacity miss here because the matrix transpose simply change the order of traversing rather than the size of data to traverse. So that's why for this one, we only see conflict misses. Okay, so I guess some of the slides were misaligned. What is this? Okay. So for this one, we only see conflict misses because of that. All right. So then you might be curious about, like, how much can we improve the performance? So again, go through the demo, right? So this is the demo that Zhi, you were wondering, like, how I generate these addresses. It's actually done from the program. I cast the first 100 elements and I partition the address like this through the C equal to ABS and this Python code. All right, it's in real, right? And now, okay, so last time we run the block algorithm, and you can see the block algorithm really make the execution time a lot faster. And now I'm going to see how transpose can help us. So this is the block MN transpose. So with that, all right, you see the order has been changed. And let me see. Okay, so let's see how much time it's going to spend. And in the meantime, I can run this. Oh, why is that? Really? Hello? Hello? Somebody there? Oh, let me refresh it. Stop, run the kernel, restart. Okay. And then, all right, and run this again. Okay, I believe it should be running. Oh, here we go, right? So the execution time, okay, let me compare it, right? And run this again. Okay, so see, previously, if I want to run the same size of matrix multiplication, it takes this amount of time, right? So for 1K by 1K, about 1 second. for 2K by 2K, even with block algorithm, take about 8 seconds. Now, with matrix transpose, see, half, right? Half, right? Does that give you some idea how to optimize your code now? Does that give you some idea about how to optimize your code now? All right, half, right? Half performance gain from here, right? So sometimes you were thinking about, like, a lot of people were asking about, hey, how can I start with my programming assignment? Indeed, in the lectures, we tell you a lot about how to do that. But okay, let's set it aside. So some software optimizations, right? Carefully lay out your data structure. Like, what do we demo? Row store, column store in database systems, right? Make your data structure align with access pattern, can better exploit cache locality. So for example, what do we just show? The measure transpose, right? Or implement algorithms in a more cache-friendly way. So for example, we have seen block algorithm in measures multiplications, right? So those are all the things that you can think of, try to make your code better. Now, let's move to the next topic, virtual memory. So here's the code. So I have, again, I have to, here I allocate a matrix, right? And I initialize the matrix. I try to count the value of the matrix. And then I try to count the average and print it out, right? So this is some kind of code that you probably would generate in your application or something similar. So the trick is that, right? If the dimension grows really large, the memory consumption of this pieces of code could be really large. So for example, this is 32K, right? So 32K is 2 to the 5 times 2 to the 10. And it's a matrix, square matrix. So it's actually 2 to the that, right? So we are actually consuming 2 to the 30. What's that? What's 2 to the 30? And this is double, right? So 2 to the 30 times 8. That's the amount of memory we are going to consume at least, right? So 2 to the 33. So what is this? 8 gigabyte, right? So simply this code will consume 8 gigabyte of memory. So now I'm changing it to 70K times 70K times 8 bytes. What would happen? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Here we go. Oh no. Okay. So what do you guys think? Well, one more. Well, all right. Looks like let me see. Can I sneak in your result? Because all right. So why don't you discuss with your friend for another 90 seconds? It's not up and running. Wait. Okay, it's broken. All right, let's start voting. All right, looks like we got sufficient amount of ballots in. When is the election date this year? Okay. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, what do you guys think? What do you guys think? C, the program will be killed automatically by the operating system as it used more than installed physical memory. What else? What? D. Okay, what's D? It will work. Any objection on that? Anyone be objective on that? All right, so here's the code, right? Well, we have a default value, but the argument can override that. So now I'm running it with 770K. And here's the memory I have. I have a total of 32 installed. So let's see what's happening. Other thoughts before we see the result? Do you think we will finish it? And this is on, yeah, and as you can see, it's running on top of a machine that you are using for your homework, right? So if someone is running the homework on the machine, good luck. Are we going to see it's finished? Yeah? Or are we going to see a message saying that it's going to be killed? Why do you think we will finish it? Enlarge the memory. And okay. Okay, you wrote such program in the past, right? So what if I run 2 instances of this at the same time? Does it still finish? What do you think? Oh, still not finishing yet. Okay, let's keep going. All right, so we will see the result later. Now I have a second question for you, right? I have a second question for you. How about this? So this is a simpler code. I am trying to I'm trying to create multiple instances of the program, and by using fork. And the thing is that in every fork, just make sure that I get the right pronunciation. In every forked process, they would have the same, exactly the same content. So if you are familiar with operating system, fork is like clone. So I'm cloning the running program. So now my question is like this, right? And if you look at the code, right, it created a random number in variable A. And now for those programs, I will print out my process ID. What's the value of A and what's the address of A? So regarding this, can you tell me what's the output going to look like? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so why do I not having the result slides for this sections? All right, so why don't we just discuss within the group again and see what do you guys think? All right, group discussion. What do you guys think? Oh. Oh. Oh boy, I have to redo the slides. Too many copy paste. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I can see here, well, after discussion, is still very confused. So, what do you guys think? B, 1 and 4. The printed address of A is the same for every running instances. Do you guys all agree with that? Some instances will print the same value. Then why B? You say, no, 1 and 4, they are contradiction. Print address of A is the same for every running instances. Do you agree with that? No. Why not? You don't know. You just don't agree. No, that's not a good reason. So, do you guys remember how volume architecture works? What's included in a program? What's inside a program? Instructions and data. Okay, what does that mean? If it's something that can be determined by compile time, the data location is already compiled in a program. It's already part of your program. And seeing this is a global variable. Global variable is determined at compile time. So the address of A would never change. No matter how many times you run it. How about, so some instances will print the same value of A. That's what Zixi you saw. Why?
I think it's still all the implement of rack. You said the.
But if I just have 4, do you think that's happening?
Will be fine.
It will be fine, right? So what do you think? Okay, so looks like you guys don't believe me, don't trust me. So let's keep yeah, and that's why we really need a demo. And let's see if the previous demo finished. All right, it finished, right? It finished and print out the average, right? So it's an evidence. Now let's run this one. So this is the virtualization code, exactly the same as the one that's given. And the number of total process is ATOI. So what if let me see, I'm not sure if this is going to work. Number of processes. Okay, let me say 4. See, so now I'm generating 4 instances, each with different process ID. Address of A, all the same. They are all having different values. 10 seconds later, right? 391, it has a value 186 preserved. 90, 110. 92, 156. 389, 140. They all have the same address, but the value are not overwritten before and after 10 seconds. What does that mean? What does that mean to you? 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 So is this address seen by this process the same with this address seen by this process? They all have the same address. But why different values can be preserved across different processes? Isn't that interesting? Right, so the answer is they are virtually the same, physically different. Right, so the answer is this. And that's the magic playing behind this. It's called virtual memory. All your programs are running on top of an illusion called virtual memory. So you thought I have this memory address. However, that's not the real memory address that you are operating on. So you have a program A, and you may have a program B running concurrently. And your processor, or say your operating system, would create something called virtual memory address space for process A. And for another process, another program, it will create another virtual memory space. So when you launch a program, regardless if it's launching from the same statically compiled program or a different one. So even though I'm running 2 tests of Pro. I'm going to create a new virtual address space for this tab. So when I'm running program A, right, I will be loading my stuff into the virtual address space, loading my instruction, loading my data. Same thing for virtual memory space for the other program. And right now, if I'm executing program A, the processor definitely needs to have its program counter pointing to the instruction location of program A. And then, well, if I found this stuff is not in the memory, the physical memory module that I installed, your system, when I say system here, it's a combination work by your operating system and our processor would work together to get the stuff loaded into the physical memory with the granularity of page. So this is somewhat similar to what happened in a cache, right? Remember, when we do cache, we load stuff block by block. But in virtual memory abstraction, we load stuff from your disk to virtual memory, or say to your physical DRAM that's installed page by page. And typically, the page size of modern operating systems are 4 kilobytes. And why is 4 kilobytes chosen? There are tons of reasons, but I can tell you historical reason, hardware reasons, because when we produce DRAM array, they found like 4K is a good size in terms of performance. So every time when you access 4K, it's minimizing the overhead of accessing DRAM. So that's why 4K is chosen. So every time I load 4K data or instructions from the disk, which hosts the virtual memory abstraction to the physical memory location. Then I can start working on this instruction, and the rest of the stuff would happen, as you know, in a cache. Now, if I am crossing the boundary of a page, the same thing would happen is that the system will have to load the demanding page into the physical memory before I can resume. And if I'm accessing another program, then the same thing would happen, right? So you can see with this, right? When I keep running the program, the physical memory is actually contains materials for both process A and process B without interfering with each other. Because although the illusion would actually pointing these pages to different locations in a physical memory to make sure that it's not intervening with each other. So what does that mean, right? So if you need more data, you definitely need a swap space to get a stuff kicked out. So it's pretty much like building, extending the memory hierarchy we learned, but to the DRAM and the storage level. So that's the virtual memory abstraction that we are living, right? So if you don't have sufficient amount of space in the physical memory, you have to kick someone out to the disk, right? So that's the virtual memory abstraction. So this is, well, there are many ways of managing this virtual memory abstraction, but because this is not an operating system class, I'm only introducing the most popular one called demand paging and swapping. And if you're more interested about this, 202 is the class. Okay, so now you hear the big thing here is that we need something to help us translate the virtual address into the physical location. So what happened is that, right? You see here, everyone has the same address, 601090, exactly the same, the one that I use in the demo. So for process A, this address will be redirected to its virtual memory space. And the virtual memory space will tell process A, or say the processor is executing process A to get the right location. The same thing happened for process B. So each process would have its own virtual space. So virtual memory is an abstraction of memory space available for software programmers to use. It's It's not about the amount of physical memory we install. It's an illusion. It's an abstraction. So typically, if we say this is a 64-bit machine, you can assume the processor can address at most from 0 to 2 to the 64 minus 1 byte. That's the address space that we can enjoy. And the operating system and hardware work together, and we organize the memory locations into pages. So why virtual memory? So you just saw the demo. With virtual memory, you don't have to worry about the size of program. And even though I have multiple applications that are both large, that are all large, virtual memory will deal with that. Even though I'm running programs on a machine with smaller or bigger memory, it doesn't matter. It will work anyway. So I can say, without virtual memory abstraction, there's no way pure software engineer can be a professional, because everyone has to deal with the amount of memory installed on each machine and have to write a lot of code to detect how many memory each one has and what has been occupied, or you have to do a lot of low-level stuff. So without virtual memory abstraction, there's no way people can just write their code in Python without worrying about how much memory being used. So this is so great, such a great abstraction. Right, so here is another view of virtual memory abstraction. So to maintain the mapping between virtual address and physical memory, we have something called page table. And why is it called page table? Remember, those virtual memory and physical memory locations, they are page aligned. And they are, every time when we load data, it's all by pages. So now, this is consuming, assuming this is a virtual memory space, we logically partition all your address into different pages. And whenever I want to access data, I am loading a page into your main memory. And the page table will create a pointer to say, now, this address is assigned to a certain memory location on your main memory. So that's the relationship between page table and your virtual memory abstraction and physical memory. So you can hear there are a lot of analogies that I can make between cache and memory, virtual memory abstraction, in a way that you can imagine the physical main memory as a cache of virtual memory, which is the universal storage of your data and code. And the block size is similar to the idea of page size. And the page table is like the tag array we have in the cache that's used to look up the content we have in the physical main memory. Unlike the cache, which is typically set associativity, for virtual memory, it's essentially like a fully associativity cache. So a virtual page can go anywhere in a physical main memory location to more efficiently use for the space. So now, if I want to do the address translation, like our very early idea of accessing cache, I can create a very simple naive table like this. So all I need to do is that I create a page table, and and the input would be the virtual address. And I can partition again, right? Since page size is fixed, and if it's 4K, you can assume the lowest 12 digits or the lowest 12 bits could be ignored because they are like the page offset within the same page, exactly like the block offset. So if I'm accessing something, right, then everyone within the same page would have the same prefix. So I don't have to create translation for each address. All I need is to create translation for each page. So I partition the address first, and then use the virtual page number, which is similar to the tag idea of your cache, as the index to search for the page table. So for example, here I say is 00B. So it's going to be the 11th entry in a page table. So I go there and I found this entry contains the physical page number, which tells you the exact location of the content in the physical main memory. That's how I get the physical address. So now my question would be, if I create my page table in this way, and if I have 64-bit virtual address space, how big is my page table? No. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. So this is what you guys think. So definitely we need some discussion. So go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, this is what we have. Okay, so now it's converged to B. What B? So B is gigabyte level. Why do you think it's gigabyte level? TB seems a bit too large, so it's not going to be TB. Okay, let me tell you the truth. It's going to be petabyte level. You have 2 to the 64. Each page is 4 kilobytes. And each entry is 8 bytes. 32 petabytes for one process, times the amount of process you have, if you design your page table in that way. So are we going to use that kind of page table? So that's not going to work, right? So that's the way how we have, so we have to optimize the page table first. So here's the thing, conventional page table assume here's a virtual address space. So every page in a virtual space should have an entry in the page table. So you need this amount of entries, right? So it's really big. However, if you think about how we use our program most of the time, are you going to write a program that's going to use like 2 to the 64 bytes? So we have a trick, right? And turns out, if you check your program layout, here's the usage of your memory space. So typically, our code will start with the very beginning part of your compiled program, or say your virtual memory space, and then come with the static data. So static data, including your global variables. So, and then immediately followed by your static data, there will be a heap memory section, which if you try to use function like malloc, you are going to get address from there. And then at the end, there is something called stack. So if you are making local variables, arguments, function code, the address is going to grow from the end to the top. So this is how we use the address space. So turns out when you run the program, it's very likely that here's how I gradually consume my memory address, right? The beginning, the end, they are used. But the big section in the middle are probably never used. So why should I create entries for this table's entries, right? So, and in fact, right, even though you have a program that consumes 1 terabyte of memory, it's still this amount of space that available for the 2 to the 64 bytes. So we are using very low percentage of the memory space available. So here's the page table that we have. So first of all, right, we break up each entries into pages. So there are a few reasons for that, but mostly the operating system reasons. So we break up entries into pages. So each of, okay, so the basic idea of here is that we make the page table a B tree. And now how we build up this B tree is that the end, or say the leaf node of B tree is each of this page table entry page. So each page would contain, saying you have 4K page, it will contain 2 to the 9 page table entries. That's a node. And then the thing is that we have to know how to locate these pages, right? So, well, so the idea here is that whenever, instead of I create all entries, I only create page table entries whenever the node is created. So that's why, so in this case, right, I only need the node for the beginning part and the end part of the program. However, what's really annoying in the tree structure is that how can I find this leaf nodes, right? So it turns out that we have to build a B tree to organize them. So the B tree idea pretty much looks like this. So thinking about that, right? If I have 2 to the 64 address space, I have 2 to the 52 number of pages that I have to address, right? And if each page can only allow you to store 2 to the 9 entries, right? Remember, B tree is a structure that a node can have links to a few number of the entries. But if I limited the node size to be a page wide, then it turns out that each B tree node can only store 2 to the 9 entries. So I have to take a 2 to the 9 as my base of the log. And turns out that I will create 6 label B tree for the page table. So what will happen is that your page table is actually a B tree structure like this. So if I want to perform address translation, it's essentially traverse a B tree. So first of all, in x86 processor, there is a CR3 register pointing to the root node of a B tree. And then this root node of the B tree would tell you what's the next level index or the next level B tree that you have to traverse. So well, as we said, we have 6 labels, right? So I also have to partition my address accordingly. But in x86-64, they also take a shortcut. As I said, nobody is going to use the full 64 address space. So actually, it's faked. Now, all your x64 processor only support effectively 2 to the 48 memory address space. So it's only using 48 bits. So ignoring the top 16, the remaining, the first 9 bits will be used as the L4 index. And this is the first, this is where in the root node that you may find the next level translation of the B tree. So gradually use the L3 index, you will find out, well, this is where it should be in the next level, and keep traversing, right? Until you reach the L1 index, that's where you are going to find the physical page number of the data. So that's the address translation. However, as you can assume, this page table is large, right? So every of this traverse of the B tree would create a main memory access, which takes hundreds of nanoseconds or hundreds of cycles in your process. So it will be really slow, right? You have to fetch an instruction first and access data. If you have no luck that both of them are currently not in the cache. And also you have to traverse the address anyway, right? Each operation would take thousands of nanoseconds. It doesn't matter how fast your processor is. So we have to avoid the address translation overhead. So it turns out here's the solution. We need something called translation look-aside buffer. The very basic idea of translation look-aside buffer is that we add a small buffer between the register and the L1. So whenever you have an access, the TLB will give you the translation. So the translation look-aside buffer is a small cache that only caches page table entries. However, as you could imagine, the bad thing about this design is that now every access has to go through TLB. So it will be terribly slow, right? So we don't want it. So another idea is that, well, can we assume the cache use virtual address? So when I execute a program, I load the address using virtual memory address without the address being translated. And then in the meantime, I consult the TLB to find the location. Does that work? Do you remember the demo we have? We have multiple processes, but they all have the same virtual addresses. Do you remember that? So it turns out if you have a design like this, we won't be able to distinguish if the cache content is for this process or not. All right, so this is not going to work. So this is not going to work. So what's the mainstream architecture right now is something called virtually indexed, physically tagged cache. So the idea of virtually indexed, physically tagged cache is very, very tricky. Remember, and that's why you really need to learn C equal to ABS and figure out the whole process of cache access. Remember, right, when we try to translate virtual address to physical address, which part remains the same? Which part is not translated? Page offset, right? So page offset is not translated. So that's the thing that is the same between physical memory and virtual memory. So no matter it's using physical memory or virtual memory, that part is the same. So the idea of virtually indexed, physically tagged cache is that, what if I use this part as the hash function to get my index of accessing cache? So no matter it's virtual address or physical address, I would have go to the same set index to look up the content, right? If it's there, it must be there, right? So the idea is that, okay, what if I let set index and block offset, this two, aligned with the page offset? right? So you can still look up your cache at the same time when you perform the TLB access, right? So I still go to the same set index to look for the block that I'm looking for. If I can make the block offset and set index completely fall within the unchanging part in my virtual address. So now the remaining part of your address, that will be the tag, right? If you make the block index and set index and block offset exactly the same number of bits as your page offset, it's essentially the tag as your physical page number, right? So if the tag I stored is coming from the physical address, and I can perform the translation of page number the same time when I access the cache, what happened is like this. When I give an address, this is the virtual address, and I partition it into offset index and virtual page number, I still use the index and block offset as usual. And in the meantime, I get a tag, which is stored using the physical memory location when the cache block entering the cache. And in the meantime, I also access the TLB to figure out the translation of this to its physical page number. And if both outcomes are equal, I know this is a hit. Otherwise, it's a miss. So that's the idea of virtually indexed, physically tagged cache. However, this guy has some limitations. So first of all, right, C equal to ABS. And remember, we want to force the set index and block offset to be completely fall within the page offset boundary. So it turns out your log B plus log S has to be 12, right? And what does that mean? If you use C equal to ABS, and if B log B plus log S is 12, it means that BS times together would be 2 to the 12. Turns out your cache, if it's a direct map one, it can only be 4 kilobytes. Right? So because we have limitation on time. So saying that, if I really want to build a cache with 32 kilobytes, right? What's the only choice we have is right now. I have to make sure, again, log B plus log S equal to 12, right? And C equal to ABS, then I can either make A equal to, if I want to build a 32 kilobyte cache, the only choice that is that the weight associativity has to be 8. So that's why Core i7, its cache is exactly this configuration. AMD Ryzen, exactly this configuration, because that's the way how we make the address translation effective with TLB. So everything is kind of connected, right? All right. So now about me, I know you care about this a lot. Multiple choice times 15. I will have some short answer questions. I will have homework style correctness questions. And you have to clearly write down the original form of the applied equation formula. Just giving the answer is not giving you full credits. You can assume the grade in assignment 1. Okay, if you have that mindset, you know what to do. Okay, don't say that I didn't tell you. You will have some credits for right, even though the final number is not correct. But I mean the outcome without saying the reason, you're not getting the credits. It's going to be a long midterm. And the reason why it's going to be long is because I don't want you to cheat. And I will make sure that nobody has time to cheat. Yes, because, well, you know, like colleagues among us, we were discussing like how to deal with cheating. Lockdown browser, student complaining about, oh, my computer crashes. We don't know if it's true, right? The best way is that you just make the exam super long and everyone get that long exam. So it's fair. So if you don't finish it, that's okay. Because if you believe everyone is like you, then a lot of people won't finish it. Right? Like a lot of you think, well, assignment 1 grading is too harsh. And in fact, no one gets full credit in assignment 1. Right? And remember, the class, we grade everyone based on your relative ranking in the class rather than the absolute grade. So don't worry about that. Make sure that you are on top of your class, then you will be top. Okay? All right. So what a sample midterm will look like. So I listed a few interesting multiple choice problems that you should definitely review after the lecture today. And also, and some of them you can find answers easily, some of them you can't. But like for this program, right, we don't have that question, but it's definitely something familiar if you started your assignment 2. And some of the programs, some of the problems that we already talked about. Some sample short answer questions, and by short, I mean try your best to limit the number of words you have within 30 words. So I have trouble reading very long sentences. And if your answer is more than 30 words, you won't get credits. You won't get credits. I will make this clear. And in fact, one of my professors, when I was a sophomore, he said, I think he said one thing that's really correct. He said, if you cannot say something within a single sentence, if you cannot explain something within a single sentence, it means that you don't understand that. I like that, right? So try to find the most succinct words to describe this problems. And I'm going to select 4 out of this to be your short answer question. So you have plenty of time to think about what are the 30 words if I'm asked this question. Question? I mean, it's online, right? Can I restrict? Okay, so this question you might be familiar, right? So you should know how to do it. This kind of question, we have that in a slide. We have this question in a slide, right? So you know how to simulate this, right? But one more thing to think about, right? Without changing the hardware, how can you improve the performance? And of course, it's based on different hardware configurations. So you might have to think about what kind of optimization would be applied. And the thing is that the question here, well, so for the short answer ones, I will definitely make sure. Okay, so find your 30 words that's different from each other, right? But for this part, I would change some of the numbers, some of the code. So don't expect they to be 100% the same. The reason why I put them here is because for this question, at least you can find the answer from our course slides. So assignment 2 still due this Friday, because I want to make sure that you at least go through all the materials for you to prepare for the midterm. And you know that our assignment is designed in a way that when you do it, you also can review the material. So it's doing the assignment actually helps you to go through the material easily and make sure that you have all the high level concepts. Midterm is actually next Sunday and Monday. The scheduled time for from the school is Monday. So that's why I want it to finish by Monday, 12 p.m. So at least some of you, if you want to go trick and treat, you can go, right? And you can take the exam any 80-minute slot between 12 p.m. and October 30th until 12 p.m. October 31st. So if you submit on 12/01 October 31, you got 0. Okay, so you have to submit before the deadline. And that's about it. Other than that, enjoy the rest of your week. I will see you next Wednesday.
I've been told by